last type of transformation you have to record on your sheet, but it's the most complicated one, which is why it got left till today. So stretches and compressions are the last thing. You should write it maybe like right here. So the reason why they're more complicated. Let us get through this, and then you guys will have time to work. So the reason that they're more complicated is that stretches and compressions can happen in different directions. And so you can't just look at a graph and say, oh, the graph was stretched. One direction it might look like a stretch, and another direction it might look like a compression. Okay? So you don't have to write this part down, but just to give you a visual, let's say I have a parabola like this. And then it gets transformed to look like this. So this could be a stretch or it could be a compression. It depends on your perspective. So there's like the vertical world and then there's the horizontal world. How we're going to decide which one we're doing is where the number is in the equation. So we'll decide whether it's horizontal or vertical based on the whole. Is it inside the function or is it outside the function? Okay? But looking at this, if I wanted to turn the blue graph into the red graph, I would kind of have two options. I could either grab a hold of the paper vertically, and if I was holding it vertically, would I be compressing or stretching to turn the blue one into the red one? Stretching. So this transformation could be called a vertical stretch. Okay? However, if somebody else looked at it from a different perspective and they were kind of thinking in the zone of horizontal stuff, they wouldn't be grabbing the paper at the top and the bottom. If they're thinking horizontal, they would be grabbing the paper on the left and the right. If I wanted to turn the blue parabola into the red parabola using something horizontal, would I be stretching it or would I be compressing it? Compressing it. So it gets a little confusing because what one person might call a vertical stretch, another person might call a horizontal compression. So the way we're going to be consistent is we're going to look at where the number is in the equation, and if it lives kind of in a certain part of the equation, we're going to say that's horizontal, and then we're going to start figuring out, does that mean stretch? Does that mean compression? What number do I use? If the number's kind of outside, we'll say, okay, that's in the vertical world. Is it a stretch? Is it a compression? And what number do I use? Okay? So you can't just say stretch or compression. You really have to label it as vertical or horizontal because it would be different depending on the different perspective. Okay? So let's talk about the vertical stuff first because you've seen the vertical stuff with the a values in the absolute value function. So for there to be a vertical stretch or compression, you would want a number multiplying your function. So in like the notation that most of you probably don't like, it's going to be having a sad technology week. Okay. Oh, there we go. And then not up here. It needs new batteries, and I forgot to bring them today. Okay. It worked? But it won't work now. Come on. Let's see. Oh, okay. It's really ugly. Sorry. Okay, so there's a number out here times the function. Okay? Yeah, it's supposed to be a. It doesn't really matter what the number is, but. Okay, the way you've seen this before is like when there was a 3 multiplying on the outside of your absolute value function. Okay. Now, if you look back at the rest of your notes, all of the vertical stuff happened outside the function. And what we meant by outside the function is if it's absolute value bars, it's not inside the bars, it's on the outside of the bars. Okay?
So under the vertical, is that
A, yeah. And then f of x. So it's like a number, but the number's not inside the function. It's like multiplying before the function. So it's like the number times all the stuff in the absolute value bars. Okay? So that will make it vertical. So anytime you see a number out here, you're going to be like, okay, that's vertical. Now to decide, is it a stretch or is it a compression? Okay? So there's 2 categories. Okay? If you look at the value of A, notice I put absolute value bars around the A. That just means I don't care about the positive or negative part of it. I just want to look at the number part of it. If the number is bigger than 1, okay, like this that you saw in absolute value, it took your absolute value graph and it made it more narrow. Vertically, that's stretching it. Okay, so in the vertical world, when the number is bigger than 1, this is a stretch. Okay. For absolute absolute value, it's like the slope. For things that are curved, we can't really use an exact slope, but we'll still use the number just in a different way. Okay? And then if the number is less than 1, it would be a compression vertically. Okay? So again, if you see a number multiplying your function, but it's not inside the squared or inside the radical or inside the absolute value bars, if it's on the outside, you're going to call it vertical. If the number is bigger than 1, stretch. If it's smaller than 1, compression. And I'm not talking about negatives and positives here. Okay? Because what did negatives do to the problem? They were a different transformation. What transformation did we do if there was multiplying by a negative? Reflection. So that's taken care of in that world. So then we can kind of ignore the negative when we're talking about the stretches and compressions. Okay? So that's all for the vertical stuff. So for the horizontal stuff, this time the number would be multiplying inside of the function. Okay? So that means it would show up multiplying inside of whatever was happening with x. Now the absolute value function is kind of a bad example of this because remember when we saw a number inside the absolute value, there was a way for us to really easily get it outside of the absolute value. And that's why we didn't deal with any horizontal stuff. Okay? But then we saw with the greatest integer function that it was much different. So like one example that we saw of this is we did this graph. Okay. And because this number was inside of the function multiplying x, it affected a different part of the function than when the number was on the outside. So if you remember with the greatest integer function, when the number was on the outside, it made the steps further apart vertically. That's because it was vertically stretching it. When the number was on the inside, okay, it was changing the length of the steps horizontally. Okay, but everything in the horizontal world is kind of weird. Like remember if it said x plus 3 inside of here, we didn't go to the right 3, we actually went to the left 3. Okay, so it has another weird thing when we look at stretches and compressions. It's kind of the opposite of what we would think. So what this means is when the b value is greater than 1. So you tend to think, oh, if something's bigger than 1, it's going to stretch it because we think bigger is stretching. But in the horizontal world, it's kind of the opposite of that. Okay? If this number is bigger than 1, it's actually a compression. And then if it's smaller than 1, it's actually a stretch. When we list our stretches and compressions, we usually tell somebody it's being stretched by a factor of this. Because if I put a 3 right here, it's getting stretched more than if I put a 2 right there. And if someone's going to make an exact graph, they would have to know that. So in these ones, you literally just get to use the number that's there. Like if this number is 3, I'm literally multiplying everything by 3. So in these ones, whatever A is, that's what you're multiplying by. So I would say use A as your factor. And you'll see when we do an example where that word will come up, and it'll make it a little more clear when we actually use a function. But here, you don't just get to multiply by B. Because it kind of works opposite of what you think, when b is bigger than 1, things are actually being compressed. You actually take the reciprocal of the number that's there and multiply it. So instead of multiplying stuff by b, in this case you use 1 over b, or the reciprocal. Okay? If you don't like 1 over b, if you like the word reciprocal better, you can use that as a factor. And again, when we do an actual number example, this will be a little more clear. So the horizontal stuff is all wacky, like the opposite of what you think is going to happen. And the vertical stuff is a little more clear, like exactly what you see is kind of what you're going to use or what you're going to get at the end. Okay. So this is all the notes we need on the back. This is all the general stuff. Okay. And then what we're going to do is we're going to do an example, and we're going to use our greatest integer function paper that we got last time to be the example. Okay? So we're going to actually use some of the problems on the back of it. I think. I don't know if it's the same or not. So the paper that you got yesterday. Is this one of them?
about Popeyes yesterday.
List all of the transformations that are going to happen in this graph. And in order to do that, we have to do a little bit of work on the inside of the function. See how the 1/2 is multiplying the x? Okay. That means that there's some kind of things that are a little bit in disguise in that function, and until you factor the 1/2, you're not going to see everything that's actually going on in the problem. Now, we're not going to take the 1/2 out of the brackets. We can't do that. This is an absolute value. It behaves different. So it has to stay in there still. We just want to separate it from the x and the number being added with the x. So I'm going to rewrite the function as y equals, and then in the brackets, I want to factor the 1/2 out of the rest of the stuff that's happening in the brackets and keep the -4. So this is something you're going to do every time there's a number multiplying x, even if it's just a negative, that's like a -1, you're going to factor that number out. Because if you don't factor it out, that number has been distributed to the thing that's being added or subtracted with x, which means it's kind of transformed what your translation looks like, how much to move it left and right. So if you don't factor it out, you're not going to move it left and right the right amount. Okay? So what does it look like when I factor 1/2 out of this? I get x. And then what do I get? So I had a 1, but I'm factoring a 1/2 out of it. Okay, so I always get multiple answers. So 2 is correct, but we tend to want to think 1/2. So 2 ways to think about this. Either just ask yourself what times 1/2 would equal 1. That answer would be 2. If that doesn't work for you, you can do this process every time of taking the number that was originally there, so 1 was the number that was originally there, and dividing it by the number that you're factoring out. And then you could get it that way also. Okay? All right, so we're going to look at it like this, and now our job is to identify all the transformations, and we're going to do a transformation on each graph. And if you guys see the directions on the homework, it asks you not only to graph it, but to give the domain and range, and to say all the transformations that took place. So you have to do this anyways. We're just going to do it at the beginning and then use it to help us graph. Okay? So I see 3 things that I'm probably going to have to write down. What does the 1/2 do? What does the 2 do? And what does the -4 do? Okay? So in class, I'm always going to try to be really consistent with how I do it so that people that are struggling can catch on. So what I'm going to do is I'm going to focus on all the horizontal changes first. And reflections will always be at the top of my list because you don't want to move something and then flip it. You want to flip it and then move it, okay? So we're going to list everything that's horizontal, and if there's a horizontal reflection, we would do that first. Then I'll list everything that's vertical, and if there's a vertical reflection, it'll be first in that group, okay? So that will just help you guys keep track of horizontal versus vertical if you're struggling with it. So where does the horizontal changes, where do they happen? Inside the function. So in a step function or a greatest integer function, that means all the stuff inside of the brackets is something horizontal that's happening. Okay? So there's 2 changes in here that are happening. What are the 2 changes? Okay, so there's a translation to the left too. Okay, so we would want to write that down. So we're going to move to the left 2 units. All right, what does the 1/2 going to do? Okay, so in an absolute value, it changed the slope, but now that things don't just have these nice little linear sides, it's not going to change the slope. So, but anytime a number is multiplying, it's either a stretch or compression. This is in the horizontal world. So we would say it's a horizontal, and then we have to decide because it's inside the brackets. So if it was an absolute value, we'd look for the stuff inside the bars, okay? So go to where we talked about horizontal stretches and compressions on the back of your organizer, okay? The number that we're looking at is 1/2. Is 1/2 more than 1 or less than 1? Less than 1. When the horizontal number was less than 1, did we call it a horizontal stretch or a horizontal compression? Stretch. So this is a horizontal stretch. And then we would say by a factor of, and we're literally going to write a number down that tells people like how much it's being stretched. So remember, for these ones, we wrote 1 over b, or we said take the reciprocal. So things aren't actually going to get multiplied by 1/2. They're going to get multiplied by the reciprocal of 1/2. So what's the reciprocal of 1/2? 2. So that's what I'm going to be using there. So again, I know the horizontal stuff is crazy, okay? So we're going to list it first every time and try to get through all of that stuff, right? So we've said what the 2 does. We've said what the 1/2 does. Now we can move on to our vertical stuff. So the vertical stuff, the only thing that's happening outside the brackets is the -4. So what kind of transformation is that? Down 4, okay? So what we're going to do is we're going to start with the parent graph. So you know how on each of the sheets I've given you, we've graphed the parent graph on the front side, and I told you that on the doors of your organizer, we're going to go put those in also. So those are the graphs we have to have memorized. Once we plot that original graph, we're just going to go through and do each of these things to it, okay? And once we've done each of these things to it, we'll have the graph of this without plugging any points into this function or have to know exactly what this looks like. So we have to know what one thing looks like, and that's the parent function. So like some of your homeworks in the unit will be like, write down all the parent functions just to get you to memorize what their shapes and stuff like that look like. One of our quizzes that we'll have will just be a quiz like graph every parent function, because those are the ones that we have to have memorized, and then we'll understand how these work to change each of them. Okay? So what I'm going to do on the first graph, so I told you guys it would benefit you to have a separate sheet of paper as we went through the example so you could see each change that we're going to make. The first thing I'm going to do to graph this function is I'm going to graph the parent function first. Okay? So I need to know what the original greatest integer function looks like. So you guys can look back at the front side of the handout that we did yesterday, and we plotted some of the steps. Now, I'm not going to plot all the steps. It gets a little bit messy. I'm going to plot like 3 of them, and I'm just going to change those. And then when I get to my final graph, I'll extend it in the directions it has to go. Okay? So my first graph, is just going to be the parent function. So if you guys remember, the parent function looked like a point at 0, 0, it went across, and then it had this open point at 1, 0. Then the steps were 1 unit long and 1 unit apart. So the next step started up here at 1, 1, went across, had an open point at 2. This step that starts at 0, 0, that's kind of like our vertex point in the absolute value function. It's kind of like our main step. So it's nice to have one thing on one side of it and then one thing on the other side of it, and that's enough. You don't have to write down like 100 steps to be able to transform it. Okay. So I'm just going to use those 3 steps and go through the transformations. Then on my final graph, I'll draw more of them. Okay. All right, so the first thing I'm going to do is my first transformation listed. I'm going to do all the horizontal stuff, then all the vertical stuff, and again, kind of red flag thing, if there's any reflection, a horizontal reflection should be at the top of the horizontal list. A vertical reflection should be at the top of the vertical list. So if you feel like you're going to forget that, on the back of your organizer, put a little star next to the reflection section or something and be like, do these first, okay? And then you won't mess them up. And thanks, you guys, for being patient. I know this isn't like the Creature in the Water project. It's not that fun, but we got to get through it so we know how to do it. Okay, so I'm going to take these 3 steps, and the first thing I'm going to do to them is this transformation. So I'm going to take all of the steps, and I'm going to move them left 2. So I'm going to make that a new graph, and I'm just going to take every step and move it left 2. Okay? My graph is not lined up very well, as you can see. I'm trying to fix it. So this means my main step, I'm going to go ahead and move that first. Okay? So it used to have this vertex point at 0, 0, but since it's going to the left 2, this vertex point that used to be right here at 0, 0 is now going to be right here at -2, 0. That's the shift that's happening. Right? So I'm going to go ahead and put that on here. Now there's no other change happening yet because I'm doing them one by one, which means all my steps are still a unit long and a unit apart. So once I kind of have that reference point, I can just finish filling in like, oh, there's the step. It'll end right there. The next one will start right here. And then same on this side. Okay. So I've just taken everything on the graph and moved it to the left too. Is that okay with everybody? Yeah? Okay, I'm going to copy this and paste this on my next graph because I don't have a nice large piece of paper like you guys do to see everything. All right. So this is what our graph looked like after we moved everything to the left too. So the next thing we want to do is we want to horizontally stretch everything by a factor of 2. That means, in this case, the steps are getting multiplied by like double the length that they had before. Okay? So this is our main step, like right here. It's 1 unit long from that point, but all that's happening now when we stretch it is it's going to make it 2 units long from that point. So I'm going to keep that point, I'm going to keep the point at negative 2, 0, where I had shifted it left. And again, I kind of use that one main step as my reference and then draw the steps around it. So the steps point is right here. Okay? That's the same point that I have up there. I'm not changing it. But now the step horizontally is going to grow so that it's 2 units long because it's getting that horizontal stretch. So instead of drawing my step so that it's only 1 unit long, I'm going to draw the step so that it's 2 units long. In other words, it goes all the way to there. I didn't change anything vertical about my steps. Okay? So that means they're still going to be 1 unit apart. So the next step is going to be right here. And the step before this one would have been right here. Notice again that I used that main step, the one that started at 0, 0, to kind of perform the transformation and then change the things that were around it. Is that okay with everybody? Okay. So that's my horizontal stretch by 2. So that transformation is done. So then the last thing I have to do is just move everything down 4. So again, this will be my final graph, because my transformations will be done. So here, again, I'm just going to kind of do everything around my main step. This was like the vertex point of my main step. I'm going to move that down 4. So that step now looks like this. And then the steps were a unit above it for the next one and a unit below it for the previous one. And I'll just put that pattern in here also. So then they've all been shifted down 4. Since this is my final graph, I could then show that I know what's going on and say, okay, yeah. So I know that the graph would keep going and there'd be a bunch of steps on the graph now like this. I just didn't want to draw them all during all the other work I was doing before. All right with everybody? So you see how you'd want the first one memorized, but if you can make that list of transformations and you understand how they work, you can then just do all of those things to get the final graph.
So you should always do like multiple graphs as the step, like the last one's like
the final answer, yeah. I would recommend doing multiple graphs. You'll see that as you get better at it, you might be like, okay, I get it. Like I'll do this and this together. Or I'll just erase this one and put where the new one would be, and that's fine. But if you're doing that and you're not getting the answer right, I would say go back to doing individual ones. I know it takes up space at first, but at least we can get the problems right. If we're not able to get them right, then that's not going to help us, okay? Any questions about this? We're going to do one more, and then we'll let you guys work on it. Yeah, Alexis? Uh-huh. Yeah, sorry. That was my vertex point originally. So remember that it started here at the very beginning, right? Then it got moved to the left 2. Then the step got stretched so that it was 2 units long, but the beginning point was still here. And then that got moved down 4. So it was right there. So a lot of people like to do one step. The only thing about doing one step is if you have a vertical stretch or compression, you need the other steps to change the vertical distance between them. So I always like doing 3 steps, like the main step and 1 on each side of it, so that I can put in any changes that are there if I have to. Okay? All right, can we try one more? Yeah. With some vertical stuff in it, more vertical stuff from just down 4. All right, looking at your guys' handout, I'll let you guys choose. All right. So again, I would want to start with the parent function. So I would look at the graph. I'd say, okay, those little brackets means this is the greatest integer function. And I would have memorized that in the greatest integer function, the main step starts at 0, 0, and goes to 1, and then has an open 1. Now, you guys might be like, you just went 3, but I didn't. Remember, with my graph, I'm calling that 1. Okay? And the next step is 1 unit above that and 1 unit long also. And the step before that would have been 1 unit below it and 1 unit long. Now again, on my graph, I've numbered every 3 spaces to be 1. So it might look bigger, but it's really just 1 unit long and 1 unit apart. Okay? So again, that's the parent function. Now, I'm going to want to go again through all the transformations. So we're going to start horizontal, vertical, and then go step by step through. How many horizontal transformations are there? 1. And what is it? Left 3. Okay, so we're going to have to go to the left 3. All right. That's going to be the only horizontal thing we're going to do. So then we're going to step into the world of vertical stuff. How many vertical transformations are there? 2. Okay. So somebody tell me what one of them is. Okay, so to go up 1. And what else? Yeah, so we have to get a little bit away from calling it slope. That really only works well with lines and the absolute value because it's made of lines. But with everything else, we have to get into that world of stretch and compression. So we know it's vertical. So we look on the back of our organizer, okay? Under stretches and compressions, under vertical ones, the number's less than 1. So is that a vertical stretch or a vertical compression? Compression. Okay, vertical is like more straightforward. Like if it's less than 1, it's making things smaller. If it's more than 1, it's making them bigger. Just like the plus 1 is up 1, there's nothing mysterious about it. Okay, so this is a vertical compression. We would say by a factor of. And we just use exactly what's there for the vertical stuff. That means everything in that realm is getting multiplied by 1/3. Okay. All right. Because it's an A value, so when it's less than 1, because it's in the vertical realm, not the horizontal. So we're going to go ahead and go through the transformations, okay? So first thing, go ahead, draw your second graph, and shift your entire graph left 1, okay? While you guys are doing it, I'm going to do it up here, and then you can look up and see if our things are the same thing, okay? So shift your whole graph left 1. So redraw those 3 steps. Oh, sorry, left 3. Thank you, people that are correcting me because I'm not doing it right. Okay, so I moved mine left 3 because of the way I scaled. Oh, not good. 1, I made a mistake because of the way I scaled my graph, and 2. This is my 1. My other step is not visible here. Okay, so your guys' can still be. All right, it would be like over here, something like that. Okay. All right, so are we okay with moving everything to the left 3? All right, so next transformation, we're going to move everything up 1. So I'm going to go ahead and cut and paste like I did last time so we can see both graphs on my screen. You guys have them right in front of you. So go ahead and move everything up 1 on your graph. Okay, so on my graph, this has been my one that was originally at the vertex point right here. So in the parent graph, it started here, right? Then it was moved to the left 3, 1, 2, 3. So then that point was here, and now it was just moved up 1, so it's here. And remember, my graph is scaled a little bit differently. Okay? Now, for the last one, a vertical compression by a factor of 1/3. Okay? This step is going to stay the same because it was that main vertex step. So when they say a vertical compression, all the steps around it are getting compressed closer to that main one that started at 0, 0. Okay? So that's why that one's not going to move. So horizontally, when we stretched or compressed, it changed the length of the step. Vertically, when we stretch or compress, it's going to change the amount of spaces between the steps. So right now, so this is what you're going to do for like every graph. You're going to find that vertex point that kind of stays the same. And in our graph, it's this one right here. And it's the stuff around it that you're going to change the distance. Since we're only doing a vertical compression, we're only looking at vertical distance right now. Meaning I'm looking at how far apart these things are vertically. So remember, my graph is scaled funny. How many units apart are these things vertically? 1 unit apart. I'm literally going to do exactly what this says. Compress by a factor of 1/3. I'm going to take the vertical distance that existed in the original problem, and I'm going to multiply it by exactly what that number is. So this distance is going to get multiplied by 1/3. So the distance used to be 1, but when I take 1 and I multiply it by 1/3, I get 1/3. This is the new distance that I'm supposed to make my steps apart. So instead of my steps being spread 1 unit apart now, I'm going to draw the main step in its same location, but the steps around it should now only be 1/3 of a unit away from that original step. Okay? So on my graph, so go ahead and make your last graph because this is our last transformation if you don't already have a grid there for yourself. And again, that main step is not going to change. Okay, that one that moved from 0, 0. Things are being stretched and compressed towards that specific step. So it's going to stay with its vertex at the point -3, 1. Okay? So I'm going to keep that where it was. This is right here. Now the steps around it, so to draw my step previously, when this step ended, I was jumping up 1 whole unit to draw the next step. But now after this calculation, the distance between them shouldn't be 1 unit now. It should only be 1/3 of a unit. So when I want to draw the next step, I only want to draw it 1/3 of a unit vertically away from the previous step. So when this step ends, I'm only going to go 1/3 of a unit up to draw the next step. Okay? And so then I could finish my graph now that I know how those look. I could put in more steps and say that means the next one would be here. The next one would be here. The next one would be here. And you can tell that they got vertically compressed, right? Does it look like somebody grabbed a hold of the top and bottom of the graph and squished it towards this one step? Okay? They did. That's how they all got closer together. Okay? All right, so tonight, your homework is going to be to finish the graphs that are on there. It's not going to be